Hello, today I want to talk about the pigeonhole principle. This is probably one of the most fun results in mathematics. The pigeonhole principle is a theorem. It's the theorem I have written right here. That if f is a function between finite sets, right, finite domain, finite codomain, A and B, then if A is the larger of the two sets, right, if it has a larger number of elements than B, that's what this notation right here represents, right? When you say the absolute value of a set, you mean the number of elements, right? So then if the number of elements for a finite set, right, in A, if the number of elements in A is greater than the number of elements in B, then we say F is not injective. Why on earth is this called the pigeonhole principle? Well, let's make this a blob diagram, and let's let A be a set of pigeons. So here's pigeon 1 and pigeon 2 and pigeon 3, and let's say, for example, say we have 4 pigeons, right? And then let's say B is the set of pigeonholes, and let's say, so the pigeons are flying and they're looking for a place to rest, so they have these pigeonholes that they roost in, and let's say there are only 3 pigeonholes. So I have hole 1, 2, and 3, right? Then what do you know? Well, if 4 pigeons are going to roost in 3 holes, then there has to exist at least one hole that contains 2 pigeons, right? No matter how they try to spread themselves out, there has to be somewhere. We don't necessarily know which hole it is that contains 2 pigeons, and we don't necessarily know which 2 pigeons end up together is sharing a hole. But we definitely know that no matter how they land, when these pigeons fly into these holes, right, some hole will have 2 pigeons land in it, right? So this is, if you consider this as a function, right, the function that assigns pigeons to holes is not injective, right? That's another way to say that 2 pigeons land in the same hole, right? So that's why this is true, right? Because you have more pigeons than holes, so 2 pigeons must land in the same hole. That is, f is not a one-to-one function. So f is that's the key insight here, right? The to translate this into more mathy language, right? Saying f is not injective is exactly the same thing as saying that there must exist a hole with at least 2 pigeons, right? And this is why that inequality is a necessary condition for this theorem, right? You have to have that the size of A is greater than B. You have to have more pigeons than holes. Otherwise, you could, in order to guarantee that there must exist a hole that is shared by 2 pigeons, right? If you had more holes than pigeons, well, or even equal number of holes to pigeons, then each pigeon could have their own hole. So that's why we call it pigeonhole principle. I think I'm not going to do a formal proof, right? I think the diagram is as good as this example illustrates the idea, right? This is with 4. This is in the case where the size of A is 4, which is greater than the size of B, which is 3. But there's nothing really special about the numbers 3 and 4. It is essentially the same in any situation where A has size greater than B. So it sounds, sometimes I think this is one of those results in mathematics that's kind of surprising, a lot like, say, intermediate value theorem or mean value theorem, right? Where it you read it and maybe it seems too simple to be of much consequence, but it actually proves really surprising things. It's a surprisingly powerful result. So let's look at an example of the pigeonhole principle in action. So here's a kind of simple a consequence of the pigeonhole principle. Show that among any three numbers, and let's actually specify integers, right? So we have any three integers. There exists a pair whose difference is even. This is a classic sort of warm-up pigeonhole principle example. So we're saying among any three integers, there always exists a pair whose difference is even. So for example, if you had, let's say we had 2, 7, and -3, right? So here, if I look at these, these are my three integers, right? Let's say, just for sake of kind of getting used to what this is saying, here we have three integers. So this is sort of a example in the example, right? A sub-example. And this is, we have three given integers. And what differences would I have here? Well, I could take the difference between 2 and 7. Okay, that was odd. That didn't work out. I could take the difference between 2 and -3. Okay, that is odd. That also didn't work out, right? But then I take the difference between 7 and -3. Ah, there we go. There's 10. We had an even difference, right? So there we just tried it out in one example, right? But this is, of course, not a guarantee that it always works, right? This is just one example. So let's now see how we could generalize this, right? And in particular, let's think about what made this difference be even versus these, which were odd. Well, here was the key in terms of figuring out whether or not a difference is even, right? Think about what could cause that. Well, here I had an even number minus an odd number. That's why I ended up with an odd, right? Here I had an even number minus an odd number, and that's why I ended up with an odd. But here I had an odd number minus an odd number, and that's why it ended up even, right? Odd minus odd will be even. So odd minus odd, that's one way this could happen, but it also could happen because maybe I had even minus even equaling even, right? That also could have been, it wasn't in this example, but that also could have been something that would have led to an even difference, right? If I had two even numbers. So what you could say here is, all right, the critical thing is that among the pairs that I pull from these three numbers, I need to be able to find a pair that's either both odd or a pair that's both even. So how can I guarantee this? Well, let's now do the argument in general, right? I've identified that key property that needs to be shared between two of my numbers. It's either oddness or evenness, right? So here I'm going to prove this result, that among any three integers there exists a pair whose difference is even. So let's let A, our set of pigeons, let's let that be three integers. So let's call them A1, A2, A3, right? Let this be our set of pigeons, right? And the A1, A2, and A3, these are the three arbitrary integers. And now let B be the set even and odd, right? So B contains just two elements, even and odd. And then I also need to specify my function f, right? So this is our set of pigeons. This is the set of holes, pigeonholes. And we also need to specify the assignment of pigeons to holes, right? So let's say what this function f is. Let f be given by what? Well, if x is even, then send x to even. F of x will equal even, right? If and send it to odd if x is odd. Right? So just f is just the function that you feed it an integer and it returns either odd or even, depending on whether or not that number was odd or even. So for example, up here in this, what would the assignment of pigeons and holes look like in this example that we had? Here's our set A is our pigeons, right? B is just odd and even. So this would look like 2 would go to even, 7 would go to odd, and -3 would go to odd, right? So here the pigeon 7 and pigeon -3 roost together in hole labeled odd. 2 actually has its own little studio apartment there with no roommates. So, so this is our assignment of pigeons to holes in this example. But we could do this in general with any A1, A2, A3, and any even odd. So, well, not any even odd, specifically with even and odd, right? They're fixed, they're not arbitrary. So what does this look like? I have now A has 3 elements and B has 2, right? And F maps A to B. So the size of the domain is greater than the size of the codomain, right? And notice I'm saying here very intentionally that B is the codomain and not the range. You could have, for example, I don't know, 2, 4, 6 are the numbers that get used, right? And if those are our integers, then they all go to even, and odd is not in the range. So there's no requirement here that B has to be the range, just it's the codomain, right? So, but point being, I have a bigger domain than codomain, right? So we can apply the pigeonhole principle. And in particular, I can say what? This A1, A2, and A3 are among our 3 numbers that are being sent to even and odd by F, right? And I don't really know who matches. So here I'm showing A1 and A2 being the 2 that get sent to the same place. But what I know is I know that F is not injective. Right, F is not injective. So what do I have? I have that there exist distinct elements, right, and which I'll just say AI and AJ, right? I don't know if it's 1, 2, or 3, right? So that's why I'm just putting I and J for the subscripts. But there exists distinct AI and AJ such that F of AI equals F of AJ. And notice when I say equals here, I don't mean a quantity, right? I mean even, I mean they're both even equals even, or both odd equals odd, right? So that's another way to say this, i.e. AI and AJ they're either both even or both odd, right? Those are the 2 possibilities here. So in either case, doesn't matter which, AI minus AJ is even, right? Because even minus even returns an even, odd minus odd returns an even, right? So we did it, we proved it, right? In either, we're now done with our proof. In either case, we found that among any 3 integers, there had to exist a pair whose difference is even, right? Now, so this is a pigeonhole argument. It's worth noting that there's a subtlety here that should be addressed. Either the problem statement could say three distinct integers, that you're really having three different integers in the set A, because if you had three integers with duplication, then A might not have size 3, right? If you repeat an integer, then you're not going to have size exactly 3, right? Sets can't have duplicate elements, right? That you can't have a element occur multiple times in the same set. So there's a technicality there. In order to claim that A has size 3, you would need that these three integers are distinct, right? However, if they're not distinct, then it doesn't add a very difficult case to the proof, right? If you had duplicates on your list of three integers, well, then just subtract the two integers that are the same, and their difference is 0, which is even. So it's still true. It's still true either way, whether you include the word distinct or not. It's just a detail that's worth mentioning, worth thinking about. So it could be that, that detail that gets you a 9 instead of a 10 on that Putnam problem, right? So this is but regardless, this is our pigeonhole principle proof here, right? So this is we've successfully proven that among any three integers, there will exist two whose difference is even. All right. Next, I want to do a slightly more challenging pigeonhole exercise. Speaking of Putnam, right? This is actually an old Putnam problem. There are lots of Putnam problems over the years that use the pigeonhole principle because it has that fun sort of clever flair to it, right? It's in the sense that there is a lot of room for creativity in terms of how you choose your pigeons, how you choose your pigeonholes, and how you choose the assignment of pigeons to pigeonholes. So I want to show this is a problem that was actually kind of an old Putnam problem. It was on the 1978 Putnam, and here's the question. So the question says that if you have 20 distinct integers chosen from the set 1, 4, 7 up to 100, right? So you have 20 integers selected from that set. That's an arithmetic progression going up by 3s from 1 to 100. Show that any selection of 20 of these will contain a pair that sums to 104. That's our goal here. So I wanted to not just show the complete proof, but I want to talk a little bit about the discovery process, right? How you might come up with your selection of pigeons and holes in this assignment of pigeons to holes. Right? So here's a strategy that you might pursue here. Just start playing around with this set and look at ways that we could get 104. Just see if you can experiment a little bit, right? This is not really a formal part of the argument, but just some experimentation. So kind of staring us in the face, there is, we see, okay, 4 plus 100 equals 104. There we go. As we're looking for, that's good. That's two numbers that add to 104. But then think about, this is an arithmetic progression, right? That we're going up by 3. So I could get another pair if I go up by 3 from 4, but I go down by 3 from 100, right? That would also give me 104. The total is the same because I added 3 to the first and subtracted 3 from the second, right? I could go 10 and 94, right? That would also give me 104, right? I could go 13 and 91, right? And so on. So there are quite a few ways to get a 104 out of 2 of these elements in our set. right? And this will continue until when? When does it kind of stall here, right? What would the last item on this list be? Well, you could have the you basically you want to get to the, think of what the halfway point is probably the easiest way to think of this. What would balance this out, right? So you would stop at 52 plus 52, right? That would equal 104. But you have to ask, is this actually on our list? Is this actually a valid choice? And no, it's not, right? 52 is in this set, right? If you look, for example, because we're going up by threes, right? So if you go from 22 to 52 is a jump of 30. So you can go up by threes to get from 22 to 52, but you can't do 52 plus 52 because why? Well, we said we have 20 distinct integers chosen from this set. So you can't choose 52 twice. So you have to take one away from that, right? So you can go down to 49 plus 55, right? That would be actually the last valid pair that gives us 104. So we actually now have all the ways listed out that give 104. That a pair of elements from this set could give 104. So note that this, right, this one is not valid, right? The pair has to be distinct, right? So this is not a distinct choice. So now let's look at this a little bit and let's figure out how many items are on this list, right? So here, what do I have? I actually have, this is maybe the easiest way to think of how many items there are on this. This is, what's another way to say 4? Well, 4 is 1 plus 1, 3. Right? What's another way to say 7? Well, it's 1 plus 2 threes. What's another way to say 10? It's 1 plus 3 threes, and so on. And why am I writing it like this? Well, finding this this way of indexing all of those numbers, it'll give me an easy way to count this set, right? Because I can continue this 1 plus 5 times 3, 1 plus 6 times 3, and etc. Right? Just writing this as an arithmetic sequence, right? Look at those numbers as a arithmetic sequence up until you get to this very last one. And what is this? That's how many threes is that from 1? Well, it would be 16 threes, because 16 times 3 is 48, and then the 1 gets you up to 49, right? So now I can see exactly how many pairs there are, right? If I'm looking at these valid pairs, I can say there are 16 pairs of numbers that add to 104 in this collection, right? Because just look at this number right there, and you can count them up. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, right? 16. So there are 16 of them, 16 pairs, right? So there are 16 pairs of numbers that add to 104. Now, notice here, what numbers are in this set that did not appear on this list of valid pairs? Well, 52 is useless, and also 1 is useless, right? I don't have a 103, so I can't add 1 to anything to get 104. So here we have to note that 1 and 52 itself, those are not able to be used in such a pair, right? In a pair of distinct numbers totaling the 104. So 1 and 52, those don't help us, right? So here's now a way that you can look at this. You could say, okay, here's another note. Another note here is, okay, 1 and 52, they don't help us get to 104, right? But I'm picking 20 distinct numbers from this set. So, all right, out of 20 numbers, and any choice of 20 numbers, at least 18 of them will be chosen among the numbers that are useful, right? Because worst case, maybe you pick 1 and 52, right? But maybe you've chosen those numbers, right? But any choice of 20 numbers from this set, 1, 4, 7, up to 100, will contain, and here they're distinct, right? Of distinct elements from this, will contain at least 18 numbers selected from this set without 1 and 52. Right, we've thrown away 2 elements, 2 options that we were pulling from. So out of 20 numbers plucked from that larger set, 1, 4, 7, up to 100, at least 18 of them will be chosen from the numbers that do not include these useless ones, 1 and 52. So now here's what I'm going to do. I have my, so now I'm ready to, with all these observations, and these you might, in a more formal setting, you might call this something like a lemma, right? A lemma means a observation or a small result that usually helps you prove the proof you're actually trying to write later. So here's, given all of this, here's now a proof. So let A be the pigeon set, right? Be the 18. Let A be 18 numbers, 18 distinct numbers chosen from 1, 4, 7, up to 100, not including 1 and 52, right? So chosen outside of 1 and 52. Right? Now, what then should B be? Well, I want B to be the set of pairs that add to 104, right? These, I want B to contain right, sets of size 2, right? So B is a set of sets, right? Our pigeonholes are these pairs, 4 and 100, that set of size 2, 7 and 90, 97, that set of size 2, and so on. So B is going to be all sets that look like pairs that add to 100 and 104. And where does B end up? It ends up at 49.55. So there's our set B. Or another way to write B is in this sort of parameterized form that we had a second ago. Right, so this would be 1 plus 3n, right, on the one side. And on the other side, it was, what would it be? It would be 103 minus 3n. Where n goes from 1 to 16. Right, that's another way to set up this set. All right, well, now we can see what are the sizes. Well, A has 18 numbers in it, and B has only 16 elements, right? So A is a larger set than B. So we have our pigeons and our holes, right? We have A, this is our set of pigeons, right? And we have our holes, right? What's our assignment? the assignment of pigeons to holes. What's our function? Well, what wall do we have in A? In A, we have 18 numbers chosen from this set 1 through 100 without 1 or 52, right? So, well, 147 up to 100 without 1 and 52. So A could be, A could be, it could have, say, 85. It could have 7. It could have, right? And I'm not sure which ones are in here. 49, right? So there's some choice of 18 numbers sitting here in A, but they're all numbers selected from this set 147 up to 100. That's what's in A. And B, what is B? B is this set of pairs, right? So in here I have 4, 100 is a pair, right? So B is a set of sets. I have 7 and 97 is a pair, and so on, all the way down to 49, 55, right? So these are the 16 sets, right, that constitute the element of B. And what is F? F, I want F to assign each number to the subset that it's an element of. So, for example, 49 would get mapped to the set 4955, right? Because it found itself, it's an element of that set over there. 7 would map itself to 797, right? 85, there would be something down here that 85 would map itself to. 85, here we have actually written down up here, 19, 85. That's what would get written here. So this would be 19, 85. That would be the set that 85 would get mapped to. So each set over here, each element over here finds the set that contains it, the set of two numbers that contains it in B, right? That's how we can construct this assignment, right? So we can say that in particular, F of A, right, equals the set in B that contains A, right, that contains that element A, right? So that's the mapping, right? The assignment of pigeons to holes. And if you want, you can make this a little more explicit, right? You could say that right, we have this parameterization of our elements, right? So you could say that it's F of A gets mapped to A, comma 104 minus A, right? If A is less than a certain amount, right? If it's less than the halfway point, so was that 52, right? And otherwise it gets, right, if it's bigger than 52, then it gets mapped to, oh, wait, I guess it still gets mapped there. Right, I guess that actually describes all of them, right? Yeah, if you have, let's see, right, if we had 7, we map it to 7, 97, that works, if A is 7, right? And if it's 85, then it gets mapped to 85, comma 104 minus 85, which is 19. Yeah, no, that actually works just fine. There we go. So ignore, I was about to do piecewise based on whether you were above or below the halfway point, but it doesn't matter because order is not important on the elements of these pairs, right? So that's a, there we go. There's a more formal way to say it without any case distinction, right? Is F of A is the set A, comma 104 minus A, right? All right, well now, all I need to do is argue that F maps two elements of A into the same element of B. And it does by the pigeonhole principle because I have 18 pigeons roosting in 16 holes, right? So I could say by the pigeonhole, we have two elements of A, two distinct elements of A getting mapped to the same element of B. Right, this is by the pigeonhole principle. This is essentially the end of the argument, because if you have two elements in any of these sets B, like say for example, say 97 was also here in set A, well 97 is also going to get mapped to 7, 97. Therefore, you have your two elements that add to 104, right? If you have two elements in, because that's how the pairs in B were constructed. They were all the pairs that add to 104, right? So at this point, we have right, if you have A1 and A2 for A1 not equal to A2, once again saying that F is not injective. That's another way to say this, right? What would that tell you? It would tell you that A1 104 minus A1 equals the set A2 104 minus A2, right? But if A1 and A2 are distinct, what does it mean? It means that it's not that this element equals this element. It's that this element A1 equals this element, and vice versa. This element must equal this element, right? So A1 equals 104 minus A2, which implies that A1 plus A2 equals 104. That's another way to say that. So there we have our two elements that add to 104. So that concludes the argument, right? That any choice of 20 elements from 147 up to 100 must include two numbers that add to 104, because 1 and 52 are useless, right? But we were choosing 20 numbers. So there must be at least 20 distinct choices, right? There must be at least 18 of them that are among the useful numbers from 147 up to 100, right? Meaning excluding 1 and 52. So now notice that there are 16 pairs of those numbers that actually add to 104, but we're picking 18 numbers among 16 pairs, right? So these there must exist a pair that has two of its numbers chosen among our 18, right? And in fact, this actually works with, we only really needed 17 numbers, right? We just needed it to be bigger than 16. So this problem, it actually would have still worked if this Putnam problem here said 19 instead of 20, right? This actually still would have worked just fine. The 20 was a little bit more than you needed, but it's still true for 20, right? So if it's true for 19, it's true for 20. All right, great. So there's our little pigeonhole principle exercise. One simpler problem and then one kind of trickier. Well, it's a Putnam problem, right? They're always at least a little bit tricky. So great. Thank you.